Right now, we are going to go through Chapter 5 problems. The problems we're going to look through is Chapter 5, 2A, 2C, number 5, number 9, number 12, 25, 28, and 38. So let's start by looking at number 2A. Chalk Point, Maryland, generating station supplies electrical power to the Washington, D.C. area. Units 1 and 2 have a gross generating capacity at 710 megawatts, steam pressure 25 times 10 to the 6 pascals, superheater outlet temperature of 540 degrees Celsius. The condensate temperature is T cold is 30 degrees Celsius. First question is, what is the efficiency of a reversible Carnot engine operating under these conditions? And skipping straight to C, is one of the coal burning units operates, produces 355 megawatts. How many metric tons of, with a metric ton being a megagram, full must be per hour are required to operate this unit at its peak output if enthalpy of combustion is 29 times 10 to the third kilojoules per kilogram of coal. Starting right off, we have a simple one, the efficiency problem. 2A is, the efficiency is just, can be calculated 1 minus T cold over T hot. Remember, as T hot approaches infinity, efficiency becomes 100%. And when the T cold approaches 0, it also approaches 100%. T hot is at 540 degrees C. So turning that, everything needs to be in Kelvin. So turning that into Kelvin becomes 813 Kelvin. T cold was 30 degrees C. So turning that into Kelvin, you have 303 Kelvin. So efficiency just becomes 1 minus 303 divided by 813. And that would be a efficiency fractional percentage. Your efficiency of about 62.627. So, not the best efficiency, but it's not bad. Now, 2C. 2C has very little to do with actual efficiency. We have to, it's just a conversion problem. We're given that we have 355 megawatts of energy. That's how much we must produce per hour. And we want to know what per hour. And megawatts, and we want to know how many metric tons per hour do we need to burn to get that. Well, the first thing we need to know is a megawatt is equal to a megajoule per second. That's megawatt is a unit of energy applied over time. So with that in mind, converting that, so we have 355 megajoules per second. And we're going to turn this into joules. Actually, we'll turn it into kilojoules to make it a little bit easier, and turn it into hours to make our lives a little bit easier. So 1 megajoule, there is a 10 to the third kilojoules. And in 60 seconds, there's 1 minute, and 60 minutes, 1 hour. So to figure out what type of energy do we need to generate per hour, we would need to generate we would need something like 1.278 times 10 to the ninth kilojoules per hour. Now, so that's all just calculating the sheer energy that we need to generate. Now we're given that the energy is 29 times 10 to the 29 times 10 to the third kilojoules per kilogram. So the next step is to divide this by that. So to have 1.278 times 10 to the ninth kilojoules per hour. We divide by 2.9 times 10 to the fourth kilojoules per kilogram. And that would give us units of kilograms of coal per hour. And this would give us 4.406, we'll say 9 times 10 to the fourth kilograms per hour. The last thing is to turn this into metric tons. Metric tons is, so if we have 4.406869 kilograms per hour, well, you turn this into grams. 1 kilogram is 10 to the fourth is 10 to the third grams, and 10 to the sixth grams is 1 metric ton. So you get something like 44.07 metric tons per hour. That is how you would determine that. And that is not necessarily what you'd call a calculus problem or a PChem problem. It's more of a conversion problem, but it still uses real world scenarios, which is part of what PChem is kind of based on, using real world scenarios, using chemistry to solve real world problems. So looking at number 5, 1 mole of water is compressed from the state described by 1 bar and 350 Kelvin to a state of 590 bar and 750 Kelvin. In addition, the beta, which is the thermal compressibility, a thermal expansion coefficient, is 2.07 times 10 to the negative fourth inverse kelvins, and the density can be assumed to be constant at 997 kilograms per meter cubed. Calculate the entropy for this transformation, assuming kappa, which is the isothermal compressibility factor, is 0. So let's write down some stuff we know. We know we have mole is 1. We have P. P1 is 1 bar. 0.00 bar, and P2 or PF is 590 bar. We know the T1 is 350 Kelvin, and T2 is 750 Kelvin. We given that beta is 2.07 times 10 to the negative fourth inverse Kelvin, and the density is 997 kilograms per meter cubed. Okay. Also, essentially, that's 0.997 grams per milliliter because it's water, H2O liquid. So, to calculate entropy, you're working at as a function of temperature and pressure. Function of temperature and pressure. So we have the temperature aspect is the integral of C sub P over T dt. And the pressure aspect is the negative V beta integral of dP. Now, there's one thing we don't have, and that's C sub P. However, that is probably the easiest thing to look up. That's one of those things that given in our textbook based on the fact that is water. Water, and we're going to make some assumptions. So, make our lives a little bit easier and just say, what's the H2, what's the C sub P of water liquid? H2O liquid. C sub P is in terms of 75.3 joules per mole Kelvin. So C sub P is 75.3 joules per mole Kelvin. Okay. With that in mind, let's do each part individually. Integrate this. You would get N times C sub P times ln TF over TI minus V, which is a constant, beta, which is a constant, delta P, which is PF minus PI. We got to watch out for units. But this part's easy part. 1 times 75.3. So 1 mole times 75.3 joules per mole Kelvin times ln of 750 over 350. Kelvin over Kelvin becomes, that part becomes unitless, but everything else, the units of our C sub P controls the units of our entropy. So this whole term becomes 57 point, we'll say 39 joules per Kelvin. Now we're kind of at a loss here. We need the volume. We get the beta, but we need the volume so that we can do this. But they give us density of water and that it's 1 mole. Well, 1 mole of water, water has a weight of 18 grams per 1 mole. So 1 mole means we have 18 grams of water. So the volume be V equals 1 mole times 18 grams per mole divided by our density, 0.997 grams per 1 milliliter. And then we're going to turn that into liters. And there's 1,000 milliliters in 1 liter. So 18 divided by 0.997 divided by 1,000 is something like 0.018 0.05 liters. So we're going to take next turn, so negative 0.01805 liters times beta, which is 2.07 times 10 to the negative fourth over Kelvin. And then times our delta P, which is going to be 590 minus 1 bars. But we have to do a conversion. 1 joule is equal to, we'll say there's 100 joules in 1 bar liter. So we'll have to take our result and multiply that by 100. So doing that, we got that times 2.07, 10 root negative 4 times 589 times 100. So the whole effect here is negative 0.22 joules per Kelvin. So we modify that to 0. You modify that, 57.39 minus 0.22 becomes 57.17 joules per Kelvin. And that's how you solve that one. Pretty straightforward. We look at 2 terms at the same time. Number 9, calculate the entropy, the change in entropy, the entropy total, and the entropy surroundings when the volume of 150 grams of CO initially at 273 Kelvin and 1 bar increased by a factor of 2 in an adiabatically reversible expansion, an expansion against P external, and an isothermal reversible expansion. Take C sub P sub M to be constant value at 29.14. Assume ideal gas behavior. State whether each process is spontaneous. The temperature surroundings is 273 Kelvin. So calculate the entropy system, entropy surroundings, and entropy universe in each situation. So we have a adiabatic reversible expansion, the irreversible expansion into a vacuum, and an isothermal reversible expansion where heat is allowed to exchange. So step 1 is write down what we know. We have we have 150 grams, which we can use to find the moles. CO. We have a C sub P sub M of 29.4 joules per mole Kelvin. We have a T initial 273 Kelvin and pressure of pressure of 1 bar. 1 bar. And we're not given V, but we're saying whatever V2 is, or VF, is equal to 2 times VI. That's the only thing we're given. Oh, and the surrounding is 273. So let's think about what we know. So first things first, let's find what our volumes are and what the moles are. To find the moles is going to be 150 grams divided by the molar mass, 12 plus 16, which is 28. 28 grams and 1 mole. If you do that math, 150 divided by 28 is going to be just 5.3, we'll round it to 36 moles. Save ourselves a little bit of trouble. there's 3 sig figs here. I'll keep 3 sig figs. There's 3 sig figs there. Now, PV equals nRT. So VI at the initial temperature. So VI is going to be what? 5.36 times R times 273 divided by 1 bar. So 0.36 times 273 times 0.0838314 divided by 1. The initial volume is 120. Let's say 121.7, just because it's don't like to round that. And then if we double that, we'll get, it's just 243 point, say 233.4 VF VI. Okay. Now let's look at each of our problems. The first thing, problem A, looks at a reversible adiabatic expansion. By definition, adiabatic expansions are ones where heat is not allowed to exchange from system to surroundings. System to surroundings. So, with that in mind, if delta S is equal to Q over T, and Q is 0, it doesn't matter what T changes to, because 0 divided whatever T is 273 is 0. So the internal entropy is 0 for the system. Now, because heat is not allowed to exchange into the surroundings, it's adiabatic. Delta S of the surroundings must also be 0 over T. And delta S total is going to be just the two of them together, 0 plus 0 or 0, making this a non-spontaneous expansion. Look at the reversible system. Look at the irreversible system. So part B. B, we have constant P external 0. So in this case, we can look at Q equals negative W because of, and work is equal to, so that means P delta V is the work. And if that's P delta V, that can also be nRT over V delta V. So we can solve for this. Then, of course, and the reason why we can do this has to do with the fact that on part B, it's just an expansion against external pressure. So external pressure means the internal energy. Actually, we can do this another way. Let's try this another way. If that means work has to be 0. Work has to be 0 on this. So we'd say that the internal energy is equal to Q. And Q is always going to be C sub V sub M delta T. But we don't know our two temperatures. So we might have to go back to that. So that's why we have to go back to here. Okay. So with in mind, we have 5.36 moles times 8.314 joules per mole Kelvin times ln VF over VI. So we double that. So even we don't even really need the two volumes because it's just because ln of 2. So our mole, our entropy right there becomes 30.88 joules per Kelvin. Now, because the entropy of the surroundings, what's the heat flow of the surroundings over 273? Well, it has to do with the P external of the surroundings times dV. P external is 0. See, the P external is 0, so the P external relates to the surroundings temp pressure. The P here is the P internal, which is right now 1 bar. Which is 1 bar, and so we have to take that into account. But so the entropy of the surroundings, is going to be just 0 divided by T. And once again, so delta S of the system of delta S total would be essentially, delta S total would just be 30.88 plus 0, being essentially and making it 30.88, thus spontaneous. So now in a reversible isothermal expansion, you'd have the same equation, the Q equals W and negative W nRT V. So the delta S of the system is the same thing here, where it's going to be 30.9 joules per Kelvin. No, joules per Kelvin, yeah. And so when you calculate this, the delta S surroundings is going to be literally negative Q system over T. Because of this is going to be obviously negative 30.9, meaning for both reversible expansions would have to, the delta S total would be 0, and thus they're non-spontaneous because of the reversibility. To be reversible, essentially we put in a very little amount of energy and they go one way or the other. I put in a fraction of some energy in, it goes one way. I take some fraction of some energy out, it goes the other way. So this not really a reversible reaction is one that it's kind of like a reaction at equilibrium. It's neither going to go forward or backwards. It's kind of at a neutral position. So it's not spontaneous in this case. It's not going to go forward. It's not going to go backwards. It's in equilibrium, essentially. But we can push it one way or the other with relative ease. 12 is we have 1.10 moles of nitrogen at 20.5 degrees and 6.2 bars. Goes a transformation state described by 215 degrees Celsius and 1.75 bars. Calculate entropy if this is our C sub P. And we'd also have to find out how to calculate our change in pressure. So let's write down our facts. So number 12. Our facts for number 12 are as follows. Moles. We have 1.10 moles and 2. PI, it's 6.5 bars. PF, it's 1.75 bars. TI, it's 20.5 degrees C, which is, you add 273, you get 293.65. And TF is 215 degrees C, which becomes 486 Kelvin. Our equation as follows. Delta S is the integral of Q over T, which is C sub P sub M dt over T times moles, and minus, since it's a gas and not a real solid, we can say negative NR integral of dP over P. So that becomes relatively straightforward. Now the hard part here is calculating for your C sub P sub M. C sub P sub M is a whole massive thing. So you take 30.81 over T and integrate that. And you'll take negative 11.87 times 10 to the negative third over T times T divided by T. And then you'll integrate that. And then you'll add a 2.3968 10 to the negative fifth T squared over K squared divided by T. So that knocks out that. And integrate that. And we have one last term, 1.0176 times 10 to the negative eighth T cubed over K cubed T. And that knocks that down to T squared, and we integrate that. So we divide all the things by T and integrate. So 30.81 becomes 30.81, we'll say, I'm going to say constant one. So C1 ln TF over TI. C plus C2 TF minus TI over Kelvin plus C3 TF squared minus TI squared over 2 Kelvin squared plus our constant 4 TF cubed minus TI cubed over 3 Kelvin cubed. All that is to keep the units good. We're all trying to get the units good. To get joules per mole Kelvin. Okay. Okay. So doing this in terms 30.81 times natural log of 486 over 293.65. So this first term goes to 15.52. Then we have 11.87, negative 11.87 times 10 to the third times a difference of 486 minus 293.65. Because the units of these are Kelvin and this is Kelvin, they cancel out, so we have the same units. So minus 2.28. The next one, 2.3968 10 root negative 5 divided by 2 times our 486 squared minus 293.65 squared. We're adding now a 1.80 and a one last one minus 1.0176 times 10 root negative 8 divided by 3. 486 root 3 293.65 root 3. So that's negative 0.30. So all the temperature terms, when we do all the temperature terms, work its way out. 8 plus 1.80 minus 0.30. And then we have to, don't forget to multiply by moles. So it's 1.10 moles. 15.74, and then we do that. So the temperature term comes out to 16.21 joules per Kelvin. Now our volume term. So our volume, negative 1.1 times 8.314 ln, we're going from 6.5 to 1.75. So 1.1 times 8.314 times the natural log of 6. So I'm adding a 12.00 joules per Kelvin onto this. So the total result when I add all these together is 28.21 joules per Kelvin. 28.21. Number 25. Calculate the delta S reaction for H2 plus CO2 goes to 2HCl at 870 Kelvin. Omit terms in the temperature dependence heat capacity is higher than T squared over K squared. So they want you to do this, but they're going to simplify it a little bit. So what we're going to do is we're going to calculate for H2 plus CO2 goes to 2HCl at 870. So the first step of this problem is to calculate the delta S naught, the reaction. So to do that, we need our entropies values. So I'm going to say this is 130.7. This is 223.1, and that's 186.9. So we're going to get 186.9 times 2 minus 223.1 and minus 130.7. So what is the entropy here? 186.9. 223.1 minus 130.7 gives you 20 joules per Kelvin. So we have a joules per mole Kelvin. That's how much energy this would entropy this would hypothetically have at 298. But to do this, we have to calculate your C sub P. And to do this, we're going to need our H's, our CL's, and our HCl. So to look these up in the book, you would have 22.66 plus 0.0438 T minus 1.0835 times 10 to the negative fourth T squared. And you would also have a T cubed factor, but it says to go ahead and ignore that. So doing the same thing. You have 22.85. You have a 0.06543 T over K. And we have a negative 1.2517 times 10 to the negative fourth T squared. And then for HCl, you have 29.81, negative 0.00412 T. And you have a positive 6.2231, 10 to the negative sixth T squared. So to calculate your C sub P, the same way as you would calculate your the same way you would calculate your delta S. You would 2 times this minus 1 minus this and this, 2 times this minus this and this, 2 times this minus this and this. So delta C sub P becomes 29.81 times 2 minus 22.85 and 20 minus 22.66. So 14.11, but you have negative 0.00412 times 2 minus 0.06543 minus 0.0438. So negative 0.11747 T over K. And so we have 0.00 times 2, 1.2517 plus 1.0835. You could sound like 2.459662 10 to the negative fourth T squared over K squared. There, divide the whole thing by T and integrate. And so we're going to add that effect onto the next thing. So 14.11 times ln of 870 over 298. This becomes 15.12. Negative 0.11747 times 870 minus 298 minus 67.19 plus 2.459662 10 to the fourth. Okay. Fourth divided by 2 times 870 squared minus 298 squared. And then, so that we're adding another 82.16 onto that. So the total contribution from the temperature change is we're adding another 30.09. So we have 20 joules per Kelvin, and we're adding another 30.09. So essentially 50 joules per Kelvin. 50 joules per Kelvin, 50.08 joules per Kelvin. 50.1 joules per Kelvin to do this reaction at 870 as opposed to at 298. The amino acid glycine dimerizes to form dipeptide glycyl glycine. According to the reaction, 2 glycines equals glycyl glycine and water. Calculate the delta S of the system, delta S surroundings, and delta S of the universe at T equals 298. With useful thermodynamic values as follows. The delta H formation of glycine is 537.2. The glycine is 746, and water 285.8. And the molar entropies is 103.5, 190, and 70. To do this, 20, pretty easy. You have glice, 2 glice goes to gly, and water. Well, the delta S of the system is going to be the easiest thing to calculate. It's just literally going to be the reaction. So we have 190, which is the gly, and the 70.0, which is the water, minus the 103.5 times 2, which is the 2 glycines. How much entropy do we get when we dimerize, or lose in this case? And we actually increase the entropy by 53 joules per mole Kelvin. Now the delta S of the surroundings is going to be equal negative Q reaction over T. So to get the Q of reaction, it's going to be the delta H of reaction, in which we can calculate the same way. Calculate the same way in that we can say that negative 746.0 and negative 285.8. We're going to add to that 537.2 times 2. So is this endothermic, exothermic? We will find out. 746, 285.8, 2 times 2. So this is endothermic by 42.6 kilojoules per mole. So the delta H surroundings, the delta S of surroundings is going to be negative 42.6 times 1,000 to get this back into joules, divided by our temperature of 298. So our delta S surroundings is equal to negative 142.9. Let's say positive 142.95 joules. No, it's not. Sorry about that. It's negative 142.95 joules per mole Kelvin. So, with that in mind, the delta S universe is equal to, we have 53 minus 142.95, going to be, well, negative 89.95 joules per mole Kelvin. So this would be a definitely non-spontaneous process, but it can be done with certain under certain conditions. The heat capacity of alpha quartz is given by this. The coefficient for thermal expansion is given by beta is this 0.3530 times 10 to the negative 4th Kelvin negative 1, and the molar volume is 22.6 centimeters cubed per mole. Calculate delta S, the molar entropy for transformation of alpha quartz at 15 degrees C in 1 atmosphere to alpha quartz at 420 degrees C and 925 atmosphere. What happens when we greatly heat up and pressurize alpha quartz? Okay. We have for 38, our equation is just going to be delta S equals the integral of C sub P sub M T dt and negative V molar beta integral dP. Okay. However, we have to do some things. We have a complicated C sub P sub M. We have a beta. We need to find our temperatures. So Ti is 15 degrees Celsius, so that goes to 288 Kelvin. And our TF is 420 degrees C, so that's equal to 693 Kelvin. So let's start by calculating the DT term. So I'm going to jump a little bit of a step and say 94 ln TFTI. I'm going to assume we've got the integration by now. 34.31 e negative 3 TF minus TI. We have 11.30 times 10 to the negative 5th 2 TF squared TI squared. So I'm going to assume we can do these integrations reasonably easily. We've done this enough times that it's not going to be too big of a problem. 693 over 288. This term becomes 41.22. Oh, just as a side note, the reason why some of these are in improper scientific notation has to do with trying to set these constants up as the same terms. If I want all of these terms to be in terms of 10 to the negative third, that makes it a little bit easier to some extent. But it results in occasionally ones that are in improper format. 8, 9. So I can run that 13.90. And five times 693 squared minus 288 squared. So all that term goes to 22.45. Okay, the whole temperature term, 13.90 minus 22.45. So the temperature term affects it by 32.65. The pressure term, we have a volume, a molar volume of 22.6 essentially milliliters per mole, because a centimeter cubed is a milliliter. There is 1,000 milliliters in 1 liter. We are multiplying by our beta. Multiplying by our beta of 0.3530 times 10 to the negative 4th. And we're multiplying our delta P, which is we're going from 1 atmosphere to 925. So 925 ATM minus 1. So 924 ATM. And then we have to keep in mind there is in 1 ATM liter, there is 101.325 joules. 0.6 divided by 1,000 times 101.325 for 3530 10 root negative 4. Okay, so the pressurizing quartz does just about jack. 7 adds 0.075. So when we add that, make that whole term negative, you have literally 32.65 minus 0.0, well, let's say 8. 0.08. 0.65 minus 0.08 changes it to, oh no, 32.57 joules per mole Kelvin. So not a overall large change. Not overall a large change at all. Mm-hmm. So that is all the homework for chapter 5 that I have assigned. Hopefully this is relatively straightforward and this will be helpful. Goodbye.